Hello, everyone. I'm Ming-Chi Han, and this is the video explanation of homework 11, question number 2. So in this question, we are given 3 cases of f function with parameter v, and we want to know that if this function can represent an autocorrelation function of a Weissen's stationary stochastic process, or can it represent a spatial density function, a spectral density function by setting v equal to omega, or both cases are true. And we are also given that how v is the relationship between v and fv is from alpha to minus alpha. And for the first part, part A, we are given a function that fv is equal to e to the negative v with the absolute value. And to know that for the first part, if it can represent the autocorrelation function, we need to know first. Well, there are several ways to figure this out. Well, there are ways to figure this out, but the solution here states really clearly, saying that if r tau, or the autocorrelation, if it's a real Weissen's stationary stochastic process autocorrelation, then it is a even function, and r tau should be less than r0, and this Fourier transform should be non-negative. So knowing it's even, r tau less than r0, and Fourier transform is non-negative, can prove that it could be an autocorrelation function. And secondly, if the spectral or spectrum of Weissen's stationary process xt is s of omega, then it is non-negative. So to solve the first one, we have that here e to the negative v, or negative absolute value of v, is even, because in here we have that this is how v and fv, well, at least how v are well represented. And here we have e to the negative absolute value of v, so basically the curve should look like this. It's clearly that this is a even function, and with the maximum value at r0 right over here, anything beyond here should be less than what's over here. So so the first two things are proven. Let's see here. Yeah, it is even proven, and its r tau is equal to less smaller than or equal to r0. And what we need to do next is to find out about this Fourier transform. So basically, what we can do is to calculate this Fourier transform, and knowing that v is only exist between alpha, or is not a non-zero between alpha and negative alpha, instead of writing positive infinity and negative infinity, we do alpha and negative alpha. We plug the e minus v absolute value over here, and for the rest of the stuff, we can just keep on writing the Fourier transform term. And by solving this, we get to this part with alpha. Alpha, in this case, alpha is a positive value. And so 2 alpha is positive. Alpha squared plus omega squared. These two are both positive. So the entire thing's Fourier transform is non-negative. So with these three satisfied, we can prove that fv could be an autocorrelation function. And for the next part, we want to know that if it can be spectral density function, and to prove its spectral density function, we need to know that this thing is non-negative. This thing is just this thing, replacing B with omega. Once again, if we draw a curve like we had previously, but I deleted it. So with this part, we can all know that at any point is larger than 0. So oops. So it could represent the power spectrum. So for part A is solved. So to solve for part B, we are given the function that fv is equal to sine v squared over v squared. We can do the same thing like above. We draw that sine square v over v squared. We know that it's an even function. We also know that well, or let's say we can simply by looking at it, anything, well, sine v or sine, let's say tau, is a odd function. Its square is an even function, and v square is also absolutely an even function. So the entire thing is even. And we also want to know that for this part, we want to know that r tau is less than r0, which is proven over here. Tau infinitely close to 0 is equal to 1. So it's definitely larger than any of the, or equal to, larger than or equal to any of the other possible cases over here, because that's the largest number. So the second case is proven. And the third case would be to have the Fourier transform. Here I have the Fourier transform, draw like a figure. And it's clear to see that it is non-negative. So it could be an autocorrelation function. And with replacing the omega, we're replacing the v with omega, both up here and down here. We know that is definitely because it's squared. It's definitely a positive function. It's larger than 0, so it could be a power spectrum. And the third case would be to find this thing. If this thing is the autocorrelation function, could it be an autocorrelation function? And in this case, it cannot be, because its Fourier transform is not non-negative. We take the Fourier transform of that, and we have this. Well, sine alpha omega, because it's a sine function, it has negative parts, and omega is well, could be a positive, could be negative, but the entire thing is not a non-negative function, so it cannot be an autocorrelation function. And for the second part, we replace this v with omega, and it is clear to see that this entire thing is larger than 0. Well, it's either 1 or 0, larger than or equal to 0. So it could be a power spectrum. So part C for that is solved. And that's everything for this question.